take it away.
Okay, thank you very much. Welcome to Mixing Reality with Qt session by Auto. We believe that showing the idea will be the best when we show the clear example. And this is the second day of this meeting, so you probably saw our example, our setup outside of this room. That will be example we describe. Probably you know something about extended reality, whether it be mixed reality, augmented reality, or virtual reality. There are a lot of tools available. There are a lot of techniques, hardware, software, but usually you have to put them together, very often in non-obvious way to have working solution. We've connected the dots and provided the way with human-machine interface design to help developers design and OEMs improve their workflows, reduce costs, and provide more flexibility and possibilities. Let me start from the working example. So this is imagine that future of car HMI design looks like this. You have a couple of physical parts, steering wheel, display, maybe some panels full of buttons, and rest of the car and whole environment will be built using Qt and virtual reality. Maybe you know all those components, but you haven't been able to connect them together. We'll show you how we do this and how it works in practice. But before we start with technical part, let me introduce the team on stage, team responsible for the setup and for this presentation. Kamil is a senior software engineer with nearly a decade of expertise in creating user interfaces and building C++ software for embedded devices. Krzysztof is a 3D graphics specialist with more than 13 years of experience in the IT industry. He is a specialist in game development, in architectural visualization, simulation, and animation. He is also a university lecturer and writes technical articles. And myself, Łukasz, lead of creative technology. I started my career in the IT industry in the previous millennium as a C++ developer, but later I switched to people and project management. I was engaged in many projects in embedded, mobile, and web areas. We all represent Auto, a digital services company with offices in Finland, Poland, Germany, and the US. Auto has worked with OEMs, Tier 1 integrators, digital services providers since 2013, providing digital user interfaces, web application, and stuff connected with automotive HMIs. What is most important for us, currently there are over 20 million cars around the world with our software on board, including those with Qt on board. So, let's start our journey. Krzysztof, stage is yours.
Okay, thank you, Łukasz. So, let's start with 3D. Our world, our reality is three-dimensional. That is a fact. So what I want to say here is, if we want to do mixed reality, we are somehow forced to think and work in 3D. Fortunately, there is no problem. As you know, Qt supports 3D through Qt Quick 3D, which is a high-level API for creating 3D content and 3D user interfaces. Here we have an example of the dragon rendered in Qt. Okay, just for reminder, let's take a closer look. How can we build these 3D scenes in Qt? Of course, we can use QML for describing the object's hierarchy and its properties. So here we have a simple QML code, and here is an effect. That approach of the QML is more like coding, yeah, not artistic expression. That is perfectly fine. We love to code. Even more, it's somehow necessary in few aspects. But for those who doesn't like to code, there is a Qt Design Studio where we can quick build 3D scene with what you see is what you get editor. What's most important is the fact that the scene created in Qt Design Studio is in fact QML code under the hood. Okay, so let's talk about basics of 3D. First of all, we need to specify a 3D view and scene environment. Okay, so we have settings like background color or image-based lighting. We can choose anti-aliasing quality or so in here. Then we need to specify, for our user to be able to see this scene, we need to specify the camera, yeah, and its properties. Of course, we need 3D models, yeah, for that, which has properties like ability to receiving shadows or casting shadows, obviously a translation in 3D space, and materials, which are mainly constructed from textures. And then we have lights. We can use a simple one without casting shadows. We can cast shadows dynamically, but this is not so good when it comes to performance. So for the most realistic effects, we can bake lights into light maps. I've mentioned 3D models. Qt has few simple ones, like primitives, yeah, cube, sphere, cone, and etc. So if we want to use 3D models, we need to import them from our 3D modeling software. And we can use most popular formats like OBJ, FBX, STL, GLTF, and so on. We can import models through Balsam asset import tool, or directly in Qt Design Studio. And during import, we can specify properties like generating additional UV channel for light map. Maybe we can rescale, we can regenerate normals, and so on. What is important that the Qt use coordination system when the app is y-axis, not z-axis, but y-axis. Okay, and what I must say here that this Mercedes model is strongly adapted by us for the presentation. So if there are people from Mercedes, please don't kill us. Okay, I've mentioned the materials. So Qt is PBR ready. What does it mean? It means that we can specify materials, but by specify properties like color, metalness value, roughness value, and so on. We can do that by simply scalar parameters, or we can do that by textures. Okay. For color, it is obvious, pretty obvious, but for metallic is a grayscale map when the black pixel means this is no metal, white pixel means this is 100% metal. For the roughness, it means like the black pixel is super glossy, opposite white pixel is super rough. Of course, we can specify other maps, other properties. For example, normal map, which simulates details on a surface. Okay, so how can we bring this all together? We can use, for example, Qt Design Studio Material Browser and Material Editor. Where can we bring together textures and see the preview? Of course, we don't have to build our own library, material library, by ourselves. Yeah. What I mean, there are plenty materials ready to use. For example, here we have a black plastic. This is a carbon fiber material. We have the brown leather, light wood, and even gold and so on. When standard PBR materials aren't enough, we can write our custom shaders where the custom shader utilities may be useful. Okay, what about lights? As you know, proper lighting in our 3D scene may say story on itself, yeah, about the scene. So first of all, we have types of lights, and we have like directional light, which is more like sunlight, okay, when lights come from one direction from infinite far point. We have spotlight, which behaves like a light bulb, yeah, which emits lights for all directions from one point in space. We have spotlights. We have also area lights, which are similar to photographic softbox lamp, but this type is only available in Qt 5. We have also possibility to image-based lighting. Okay, when we can specify the HDR image to lead our scene, and this lighting may be independent or maybe in addition to standard lights. Okay, we all want realistic effects. Yeah, we want bounce lighting, indirect lighting, global illumination. We want soft shadows and so on. But computing them in real time is not so simple. Fortunately, in Qt, we can do this by light mapping. Light maps are textures, okay? And light mapping is a process when we render the lights. Yeah, it is like rendering, offline rendering, but instead of rendering the frame that camera sees, we can bake lights into the textures for future use in write-down. So here is an example of standard lights, and here is an light mapped effect. This effect is from the documentation. Okay, also reflections are not so simple, and in Qt we can do reflections by reflection probes. Okay, we can place the reflection probes around the scene. Then we can bake these reflections to the cube maps, and then our objects may use these reflections, these cube maps, to show reflections. And last but not least, we have some post-process effects. These effects are like effects that attach it to the already rendered frame. Okay, so when we have the frame that has been rendered, we can then attach post-process effects. So we can do distortions like that, or we can do the color grading. We can do the bloom effects, vignette, and so on. Okay, so our final scene looks like this. We've experimented a lot, and we decided to use more stylized rendering instead of realistic. We do not use light maps because of time. Okay, light mapping needs to be rendered offline. It takes some time, and for our prototype, we need to have quick iterations. So we don't use light maps. So what is our stylized rendering? It means that we have image-based lighting based on HDR image. Then we reworked some of mentioned irreal example materials. And finally, we display to the user the image that is only one color with reflections that comes from the specular roughness value from these materials. And we think that's perfectly fit our needs, our story. It is also performant, and it doesn't look flat. For more technical, for more mixed reality point of view, we've optimized a model of the car from high poly to rather mid poly. As you can see, our car doesn't have steering wheel, but for that, Kamil has more to say.
Right. Thank you, Krzysztof. So we have our scene finalized. We have our car on the scene. So where do we actually use it? So we have built a mixed reality cockpit that simulates the car interior. So what components make up this mixed reality cockpit? You can observe certain elements sourced from an actual car, notably the steering wheel and the seat. Surrounding the seat, there are 3 LED panels that are providing the proper lighting to the scene, and the PC is positioned behind them. At the top, 3 SteamVR base stations are responsible for the headset tracking. Additionally, we have the HTC Vive tracker that is concealed by the steering wheel. And what else can be identified? Obviously, the widespread green color facilitates the chroma keying technique, which I'll come back to in a moment. All of these elements are integrated using aluminum frame profiles. Last but not least, at the core of our setup lies the Varjo XR-3 mixed reality headset that drives this immersive experience. So if you are wondering what mixed reality is all about, then let me break it down for you. Mixed reality is all about merging the virtual content with the real world in an interactive way. So you see virtual elements appearing as a natural part of the real world. Now, to create the most convincing and believable scenarios, we needed to choose an advanced headset with highest possible image quality. We have researched of what's available on the market and chosen the Varjo XR-3, and it works great in our setup thanks to its video pass-through cameras. If you set up the environment properly, distinguishing where the virtual reality ends and the real world begins becomes a challenge. Varjo XR-3 supports both an accurate head tracking and support for physical trackers like the one on the right that are essential for maintaining the synchronization between those 2 worlds. Moreover, Varjo offers a great Varjo Lab Tools utility, which is suited to creating a variety of mixed reality setups without investing any more time into the actual driver development. It's great for rapid prototyping. We are actively using it in our setup, and it saved us a lot of time trying out new ideas quickly. Most importantly, Varjo is fully compatible with the chroma keying technique. I suppose everyone is to some extent familiar with this technique, as we've all seen it in movies. But for those unfamiliar, the chroma keying, also known as green screening, is a process where a specific color is removed from a video or a picture, allowing that part of the image to be replaced with virtual content. Now you might wonder why actually chroma keying? Because we have tried other solutions for achieving a similar effect, like depth occlusion using LiDAR sensors. However, we didn't get the same high quality nor fidelity. But here is the catch. Using chroma keying in an XR project isn't a walk in the park. For our project purposes, we needed to focus on certain topics. Firstly, the headset needs to be calibrated with the proper accuracy, and its tracking point needs to be adjusted and well placed within the 3D virtual environment to match those two realms together. Next, we needed to create a 3D restricted mask covering the green area. This mask indicates that everything inside it would result in a mixed reality experience, and outside of it would be a virtual reality, so that you would be able to look around and see what's behind your back. Next, the chroma keying requires a specific environment setup. That is, the lighting needs to be within the optimal levels of illuminance, with constant color temperature and with diffuse non-reflective light source. Lastly, chroma keying works best with matte fabric that reflects as little light as possible. So we've tackled all of these hardware challenges, but how did we make it happen on the software side of things? Let's have a look at this simplified diagram illustrating the overall project architecture. In the center lies the Varjo base, which is primarily used to run and manage the headset. It's where we set all of the XR3 settings, where we calibrated the pass-through cameras, and also it allows us to receive a real-time feed from the headset, allowing anyone to experience what the user of the headset is seeing during the simulation. Moving on to the Varjo Lab tools on the left, this is where we created a 3D restricted mask and calibrated the chroma keying by setting up the color and all of the tolerance values. Then the mask created with Varjo Lab tools is anchored to the physical tracker. Then the base stations are collecting data and calculating the position for both the tracker and the headset. And then all of this data is transmitted through the headset to the SteamVR runtime. And this is where the OpenXR standard comes into play. It provides the necessary API for accessing all of this data. At the end, our Qt 6.5 project is connected to the setup through OpenXR. We are actively using both the Qt Design Studio and the Qt Creator. Qt Design Studio we are using for the scene modeling, as Krzysztof described, and the Qt Creator to modifying the project and running it on a headset. Before showing you the final result from the headset, let's quickly have a look at how does the workflow look like. So we start in Qt Design Studio, where the scene is prepared by our technical artist. We can see the real outputs from the 3D viewport and the corresponding generated QML code. Now, still within the Qt Design Studio, we need to export the project by generating the CMake list files. It's quick and easy, totally supported by Qt Design Studio, and there are no problems with that. Now we need to jump into the Qt Creator, where we open the generated CMake list project. It won't run on the headset just yet. We need to rework it for the XR by adding the OpenXR support. For that purpose, we are using the great module created by Andy Nichols called the Qt Quick 3D XR. I know that Andy Nichols is here with us on the scene, so this is a really great module, and it helped us really with all of the project. Anyway, I would recommend you using this module if you are about to experiment with VR or XR in Qt. It's freely available on Qt Git repository. And if you would like to know more about how the integration between the OpenXR and Qt is done behind the scenes, I would recommend to look at the presentation from Andy on virtual reality with Qt Quick 3D from like 2 years ago. Next, if we have our OpenXR module integrated in the project, we need to actually rework it for the mixed reality to actually happen. We need to replace the view 3D with an XR view. We need to replace the camera with an XR actor and do a few smaller modifications, like removing the anchors and stuff like that. Optionally, we can add the controller support to do any kind of integration with the scene. To quickly test the environment during the runtime, we have built a sample menu that is floating in 3D space in front of the car, and it is steered by a controller. It allows us to quickly change settings like ambient occlusion, anti-aliasing, change the debug material, enable the wireframe mode, reposition the model, or rescale it. It's really great to have something like that for the runtime modifications of the scene. So, enough talking, let's see it in action. We are using the diffuse material for this video. So please have a look at how does the hands and the steering wheel look from coming from the pass-through cameras. So, and now that we have our scene and we have our hands and the steering wheel coming from the pass-through cameras, we are fully able to enhance the setup by introducing a full HD touchscreen. It allows the user to feel the actual haptic feedback coming from the touch while still being immersed into the simulation. This is incredibly useful for tasks like verifying the precise dimensions and placement of design elements, whether the user can easily reach all of the areas of the screen, or whether the HMI design matches the rest of the car interior. And if you are on the very early stage of UI development, a fully developed Qt application is not yet needed. You can use any designer tool. In our example, we have went with Figma. Additionally, there is no need for any special screen. It can be very simple and low cost, like attaching your phone or a tablet to the screen. And it doesn't even need to be a screen. It could be a panel full of buttons and switches, or any kind of hardware that matches the project requirements. Now, what's crucial when working with designs is being able to modify them during the runtime. And we have checked two workflows that are totally fine with an XR headset. One is when the designer is performing the modifications of the design remotely, and the headset user is giving the live feedback on the changes. And the second is when the headset user is actually doing those necessary modifications. So let's see how does it look like. Now we have switched to the roughness material of the car. You can see the user is verifying whether it can easily reach all of the areas of the screen. Please pay attention now that the designers in real time can, for example, lower the font or change the placement of some design elements, and the headset user can give the live feedback on those changes. Next, the headset user is perfectly fine to perform the edits in real time on his own. Now, if you are going further with HMI development and you are now producing a dedicated UI for an automotive hardware platform, so let's enhance the setup by introducing an automotive hardware as a source for the central screen that we have in our setup instead of Figma. There are plenty of dedicated automotive platforms. For our purpose, we have been playing with a few different ones that we found in our lab. That is the NVIDIA Jetson Orin, Jetson Nano, Intel NUC, and Qualcomm Snapdragon. They all work perfectly fine in the setup. We have went in the final project with Intel NUC. However, any hardware would work perfectly fine. All of these dedicated automotive platforms deliver high performance computing coming from those relatively small devices. We set the ecosystem to Ubuntu based so that we are able to run any application dedicated for this Linux distribution. Qt applications run perfectly fine, whether that is by installing the whole ecosystem on the device or by cross-compiling from another device. To showcase that the mixed reality cockpit is perfectly able to test dedicated Qt applications, we've used our created some time ago Qt 3D map demo. It allows the user to manipulate the 3D map and set the navigation using a few predefined routes. So let's see it in action. We are now using the textured version of the car. The user is interacting with the screen, which is running the Qt 3D map demo coming from the Intel NUC hardware. All right, so this brings us to the end of our journey. So let's summarize. We have talked about what are the Qt 3D possibilities in terms of materials and lighting that helps us in building the immersive 3D scene. Following that, we showcased a complete mixed reality bug or other called a cockpit, and went through all of the software and hardware challenges that we had in our project. Later, we enhanced the cockpit by introducing the fully interactive display featuring Figma. And next, with the automotive device running the 3D map demo. The journey has culminated in the creation of a fully immersive mixed reality experience. Simply put, Qt Quick 3D is fully capable of handling such projects. Łukasz, please say some final sentences.
Okay, there was a lot of technical information. Are you lost? Don't worry, we can repeat everything, or at least answer the questions at the very end. So let me summarize the work from a little higher level, maybe from a business level. Why we build this cockpit and who and for what can be used? First, our idea was to interact with physical elements. So we built the cockpit with physical steering wheel, physical display to have fully immersive experience in mixed reality. Of course, as guys mentioned, we can add next elements to that. The second scenario we consider is to interact with virtual elements. Of course, interacting with virtual elements is not as immersive as the physical ones, but with our setup we have quite good tools, as you can see, for hand tracking and seeing your own hands. The third simulation scenario we had in mind was to simulate driving. Of course, this is not implemented yet, but we consider it for the future. So, as you can see, tools are quite powerful, and in fact, next scenarios are limited only by your imagination. Okay, one slide maybe from the business perspective. What are the benefits from such setup? Benefits for OEMs, designers, developers. So first, of course, we can, with those tools, improve our workflow. We can move some part of the work into the virtual world. We can also reduce the cost and time to market, again, by moving some part of the implementation to the virtual world and move some experimentation also there. And instead of making iteration with the physical stuff, we can make it in the mixed reality. Finally, we have, of course, a lot more flexibility, and we can also explore new possibilities. We are not limited to the physical elements. We can do more. So possibilities are limited only by your imagination. And for the future, what can be also done with this setup? Of course, mentioned driving experience, we can add to this setup that element. That should be quite easy. This is Qt project, so it's doable. Next, we can add real road traffic around the car, and with that start testing driving scenarios. For example, we can test autonomous driving experience. Next, we can collect biometric data from Varjo headsets like eye tracking or from other sensors and analyze driver behaviors in various situations. Of course, more automotive hardware is also possible. We can test next car components in the mixed reality setup. And we are from the automotive industry, so car simulator is natural playground for us. So we choose to build the car simulator, but of course you can build something else. You can build boat simulator, plane simulator, or even spaceship simulator. In fact, possibilities are limited only by your imagination. So if you have other idea how this setup, those tools can be used, but you are not sure how to implement it, come talk to us. We can help with that. And with that, that's the end of our presentation and time for QA.